You have 23 chromosomes, and they come in pairs because you have two parents. So that means you have 46 total, right? So if we look at one of those pairs of chromosomes, we're going to say this is from mom, and we're going to say this one is from dad. Now on these chromosomes, you have genes. So we're going to just use gene E as an example. We're going to say that having a dominant allele means you have small ears. And we're going to say the lowercase e means you have big ears. So in this case, if this is your genotype, you would be a heterozygote. In this case, the dominant E would trump the small e, meaning that you would have small ears, and the recessive allele would be hidden. You are capable of this heterozygote genotype because you are diploid for this gene, because again, you have a mom and you have a dad, and you have their combined genetic content. So, not all genes are like this. In this instance, gene E was like this because this is on what is called an autosomal chromosome pair. But again, there are 23 pairs. On the 23rd pair, there is something different going on. On the 23rd pair, mom is different than dad. And so actually, I'm going to duplicate these so it's more obvious what I'm talking about. On mom's chromosomes, we have the X chromosome. And then on the father's chromosome, we have the Y chromosome. And so the Y chromosome is different than the X chromosome. This is only true for this pair. All other chromosomes are identical in the number of genes they have. On the 23rd pair, however, there is genetic information missing for males. And so if you are a woman, you have two X chromosomes. Now let's consider the disease that is discussed in this question. It is asking about hemophilia. Hemophilia is a recessive trait, so I'm going to use a lowercase h to represent its allele, and I'll use an uppercase H to represent being normal. In case you're curious, hemophilia is when a blood clotting factor does not work. Blood clotting factors help you to get scabs, and it helps to seal wounds and prevent internal bleeding. Having hemophilia means that you repetitively will bleed with very little stress. You can bleed internally with your joints, or if you get a cut on your skin, you could bleed externally, and you could die from bleeding too much, basically. You can't stop bleeding. It's a pretty terrible disease that I believe originated in Russia due to inbreeding of royalty. And so anyway, let's say that you are a woman. And let's say that you are unlucky enough to have some Russian blood in you. And I'm drawing the little h here twice because this is a duplicated chromosome. But on this particular chromosome here, you have the recessive gene. Luckily, you are a woman, so you have two X chromosomes. That means that the other one could have the dominant form. This means your genotype is heterozygous, which means you are normal. Lucky you. However, if you're a man, you don't have that same luxury. If you are a man, you will have an X chromosome, and you will have a small little Y chromosome that is missing genetic information. And so if you are a man and you are unlucky enough to have the recessive gene, you do not get a second chance. So for the women, they are diploid for these traits, meaning they have two sets. Di means two. For the man, they are only haploid for these traits. I just like to remember haploid half. They don't have a second chance. And so in this question, they're asking you, what would happen if a mother was heterozygous? So instead of drawing those chromosomes over again, I'm just going to draw an X for the female. And I'm going to say that this is her genotype. She is heterozygous. And then it says, what is the chance that she will have a son that has hemophilia? And so this question seems tricky because they don't even tell you what the father is. They tell you what the mother is. So we could start a Punnett square. And we could try to figure out what the chances of having a son with hemophilia are. But then when we try to draw the father in, you might be asking yourself, well, what about the father? What about his genotype? They didn't tell us. Well, first of all, we don't need to know what's on the Y chromosome because there is nothing on the Y chromosome. He is missing that information. But we do need to know what's on the X chromosome, right? Well, actually, no, because in order to make a son, he has to donate his Y chromosome. So we don't even need to consider these top two boxes. They're not important. We're talking about what are the chances of having a son. So we're going to bring this down here and that over here. And so this is one possible son, and this is the other possible son. And again, we don't need to worry about these boxes here because that makes daughters, not sons. So if we only look at these two boxes here and we just forget about these two, the chances of having a son with hemophilia would be 1 out of 2, which is 50%.